Hey, this is Mr. Ferguson. I'm introducing lesson 10.4 right now, where we're going to look at Gay-Lussac's law and the combined gas law. And by the end of this lesson, we hope you can state and use Gay-Lussac's law and state and use the combined gas law. Once you've gotten Boyle's law and Charles' law kind of solidified, the rest of them start to come faster. So we'll show you these two laws and work out some example problems. Let's get started. So we set up some lab equipment to attempt to derive Gay-Lussac's law with some data, and there we took a still photo of our pressure sensor hooked up to a small Erlenmeyer flask, and it's monitoring the pressure in the Erlenmeyer flask. This is at room temperature, so we have 99 kilopascals of pressure. And I know it's probably a little bit hard to see in the photo, but the temperature is approximately 22 Celsius in this photo, which of course we need to change to Kelvin.
So the pressure, as we said, would be 99 kPa. So it's almost a nice day out. 101 would be 1 atmosphere, so it's a little low pressure today. And the temperature is 22 degrees Celsius, which turns out to be 295 Kelvin.
Which, if we want to calculate with it, we need to use the Kelvin value.
Yes.
All right. Then what we did was we took the Erlenmeyer flask and we submerged it into a hot water bath. And we tried to hold, so you can see our hot water bath.
Right down here.
And the flask is sitting in there. We let it sit there for about 10 minutes. And we've got a new pressure here, 112. And again, it's hard to see, but the temperature is approximately 53 degrees Celsius.
So the pressure, as we just said, is 112.
And we had 53 degrees Celsius, which again, we've already converted to Kelvin. It works out to... go. So now the question is, what kind of a relationship is this? Are we seeing this inverse relationship where the product of pressure and temperature is a constant? Or is it the direct relationship where the ratio of pressure to temperature is a constant? So we worked it out both ways. And if we take the product of pressure and temperature,
you get it to equal 29,000.
We get 29,000 for the first instance.
And then for the second, we get 37,000.
We get 37,000, and those aren't really the same value.
Not all that close. Okay. And then for pressure divided by temperature, we got 3.0 using correct sig figs. And then we got the next one, we had 2.91 using correct sig figs. So due to rounding, you could see that these numbers are rather similar.
These are a lot closer than the other two, so I'm thinking, and I mean, it's pretty intuitive. If we increase the temperature and the gas doesn't, the container can't expand, it stands to reason that the pressure should go up because the collisions of the particles are happening more frequently with the walls of the container and with more energy because they're at a higher temperature.
Right. So I think we determined that this is a directly proportional gas law. So let's take a look at this in the next slide of what the actual equation should be. So Gay-Lussac's law in words would be, for a given amount of gas at a given volume, pressure and temperature are directly proportional. So this means volume is held constant.
So the container needs to be rigid.
Yeah, and the pressure and the temperature will be directly proportional.
So in an equation, this is going to look very similar to Charles' law, except instead of V over T, this equation has P over T. And that's equal to a constant, so we'll call this one K3, which in a more useful form, we can say that the ratio of pressure to temperature in the first instance for the same system is equal to the ratio of pressure to temperature in the second instance. And again, knowing any three of those, we can predict the fourth one.
And of course, the graph for this would have, I believe,
So when it's a direct proportion, we plot P versus T.
A straight line.
We get the straight line.
All right, and that is our Gay-Lussac's law. All right, so then lastly for this lesson, we're going to talk about the combined gas laws, and it simply does what we just stated. It combines the Boyle's law, Charles' law, and the Gay-Lussac law. So if you remember that Boyle's law was the P1V1 equaled K1, Charles's law was V divided by T equals K2, and then Gay-Lussac's was pressure divided by temperature equals K3. And something you can do is combine them all, because one system doesn't have something always held constant. So P times V divided by T equals a constant value as well.
Whoops.
So
we called that K4.
K4.
So it's still a constant. It's just a different constant for the system now.
So what we can actually do now is just say, well, we now know that P1 V1 divided by T1 equals P2 V2 divided by T2. And honestly, this is the only equation you would have to remember as long as you remember certain things are being held constant. So if you're doing a Boyle's law, you know temperature is being held constant, so they disappear.
They just cancel they're the same on both sides, so they in essence divide out. There's Boyle's law.
Yep. Or if you know that, volume is being held constant, there you go, you can do Gay-Lussac's. Or if you know pressure is being held constant, you can...
So if pressure's constant, it ends up that the P's cancel out. It's the same value. So you have V1 over T1 equals V2. That's Charles' law.
Yeah, so this is a very important one to remember. So for a given gaseous system with a fixed number of particles, N, of course, is
I think I need
constant.
to move that up a little bit. There we go. Yeah, so as long as you're not allowing gas in or out of the system, that combined gas law works for really any situation.
I think there's two more gas laws we're going to learn about, Avogadro's and the ideal gas law.
The granddaddy of them all, the ideal gas law.
All right, let's go on to a practice problem. But you're right.
Yeah, so here are two practice problems, and as Mr. Hunter alluded to in the previous slide, what we can really do is just use that combined gas law for everything and kind of cancel out any terms that are not going to change from one side of the equation to the other. So let's look at sample problem 1. A flask at standard temperature and pressure has its temperature increased by 200 Kelvin. Predict the new pressure. So we have a change in temperature. We increase by 200 Kelvin. We're going to have a change in pressure, but because it's a flask with rigid walls, the volume's not going to change.
So the volume, therefore, will drop off.
Okay, so our equation is P1 V1 over T1 equals P2 V2 over T2. But since the volume term is going to be the same in both of them, and we don't even need to know what it is, whatever the flask volume is kind of irrelevant.
It could be 1 or a million, it'll still disappear. It
divides itself out, so we end up with Gay-Lussac's law, P1 over T1 equals P2 over T2. So now we start substituting in.
So we know 1.00 atmospheres.
1.00 ATM.
Divided by 273 Kelvin.
That's standard temperature.
Equals X, or P2.
P2.
Divided by 473.
Because the temperature went up, so we just add 200 on to the previous temperature. So 473 Kelvin. Solve it for P2.
So we multiply both sides by 473, and we find that X equals 1.73 atmospheres. Now this makes logical sense, because if you increase the temperature, you expect the pressure to go up. If you get an illogical answer, check your math.
Right, you might have multiplied instead of divided, or vice versa.
All right, let's look at the next problem then.
So this one has everything changing. It's a movable piston, it has an initial volume of 0.5 liters at 298 Kelvin, and at a pressure of 1.2 atmospheres. So the temperature is increased to 348 Kelvin, but the volume's also increased to 2.0 liters, and we are supposed to figure out what the resulting pressure is. So we're going to have to let all the terms there because everything's changing. So the initial pressure is 1.2 atmospheres multiplied by the initial volume of 0.5 liters divided by the initial temperature of 298 Kelvin. And we're going to set that equal to the second set of conditions, which is 2.0 liters multiplied by our unknown, which is again P2, and then divided by the 348 Kelvin. And again, we're still solving for P2 in this one.
And I have it to be 0.4 using correct sig figs, assuming I did my math right.
0.4?
Yep.
Don't we need it? Oh no, because 0.5 liters
0.5
only has
is one sig fig.
0.4, and the unit would work out to be
atmospheres.
And we did not show you the intermediate steps, but they do The units do cancel. Everything except atmospheres cancels out.
So this is basic algebra that you have to be able to perform and understand unit deletion as well.
And we've shown enough examples of that in class. I think everyone's pretty on board with that. But that's it. So the combined gas law gives us, and then you don't really have to remember all these different separate sub-laws, at least for ones just involving pressure, volume, and temperature differences. The combined gas law will serve you very well.
Now, this doesn't mean you don't have to know what Boyle's, Charles, and Gay-Lussac law says.
That is true as well.
It just means you don't need to remember each individual gas law if you forget them for a mathematical purpose, but you do need to know that Boyle's law is an inverse relationship. Charles and Gay-Lussac are both directly proportional. What variables they keep constant and what variables they use to calculate. These are things you do still have to know. But this combined gas law does make your life a little more easy if you forget something.
All right, we'll do lots more examples in class, so until then, have a good day.
Yep.
All right, chemistry students, your post-video question from this lab is going to involve the combined gas law. We have a 1 liter container of gas at standard temperature and pressure, and we're going to compress that container to a smaller volume, 0.77 liters, and increase the temperature to 25 degrees Celsius. What's the final pressure in the container? Caution, remember, you cannot deal with Celsius in a gas law problem, so you're going to have to do something with that before you work out the answer. Give it a try. We'll check on it in class the next time. Have a good one.